Our universe is a place of wonder and mystery. We experience it through our senses, perceiving 3 dimensions of space length, width, and height. But what if I told you there's more to reality than meets the eye? What if I told you that time itself is a dimension, intricately woven with the fabric of space? This essay embarks on a journey to explore the captivating realm of the 4th dimension, time. We will delve into the history of its discovery, understand its implications through simple analogies, and examine the tantalizing possibility of time travel. Prepare to have your perception of reality challenged and expanded as we venture into the fascinating world beyond our everyday experience. Our exploration begins with the familiar 3 dimensions, the foundation upon which our understanding of the universe rests. From there, we will journey through the annals of scientific history, encountering the brilliant minds that dared to challenge conventional wisdom and unveil the secrets of time. Imagine a simple cube. This cube, though seemingly basic, is a perfect representation of the 3 fundamental dimensions that we encounter in our everyday lives. It has length, width, and height, the 3 dimensions that define our physical world. These dimensions are not just abstract concepts, they are the very essence of how we perceive and interact with the space around us. We use these dimensions every day to navigate our surroundings, build structures, and describe the objects around us. Whether it's the towering skyscrapers in a bustling cityscape or the intricate design of a small gadget, length, width, and height are integral to their existence. A book on a table, for instance, occupies a specific space defined by its length, width, and height. These dimensions allow us to understand its size, shape, and how it fits into the space around it. These 3 dimensions are the foundation of Euclidean geometry, a system developed by the ancient Greek mathematician Euclid. Euclidean geometry has been instrumental in shaping the way we understand and measure space. For centuries, this system served as the bedrock of our understanding of space. It provided a framework that was both intuitive and practical, allowing for advancements in architecture, engineering, and various other fields. It shaped our intuition and guided our perception of the world. The principles of Euclidean geometry became so ingrained in our thinking that they seemed almost self-evident, a natural part of the human experience. However, the dawn of the 20th century brought about a revolution in scientific thought, challenging the very essence of our understanding of space and time. This period was marked by groundbreaking discoveries that questioned the limitations of the 3-dimensional world. The stage was set for a paradigm shift, a departure from the familiar 3-dimensional world into the uncharted territory of the 4th dimension. This new dimension promised to expand our understanding of the universe in ways previously unimaginable. This revolution was spearheaded by none other than Albert Einstein, whose groundbreaking theories would forever change our understanding of the cosmos. His work on relativity introduced concepts that redefined space and time, paving the way for modern physics and altering our perception of reality itself. Before Einstein, our understanding of the universe was rooted in classical physics, governed by Isaac Newton's laws of motion and gravity. Newton's Principia Mathematica, published in 1687, laid the groundwork for centuries of scientific thought. His laws described the motion of objects and the forces acting upon them, providing a framework that seemed to explain the workings of the cosmos with remarkable precision. Newton's vision of a clockwork universe, where every event could be predicted if the initial conditions were known, dominated scientific thinking for over 200 years. Time, in this framework, was absolute and unchanging, ticking away at a constant rate for all observers. It was a universal constant, much like the ticking of a perfectly synchronized clock, unaffected by the motion of objects or the forces acting upon them. This concept of absolute time was deeply ingrained in the scientific community and the public imagination alike. Space, too, was considered absolute, a fixed and immutable backdrop against which the events of the universe unfolded. It was thought to be a vast, unchanging stage where the drama of celestial mechanics played out. The positions and motions of planets, stars, and galaxies were mapped with increasing accuracy, reinforcing the idea of a static, unalterable spatial framework. However, the seeds of a scientific revolution were sown in the late 19th century, with the emergence of new and perplexing phenomena. Scientists began to encounter anomalies that could not be explained by Newtonian mechanics. These included the behavior of light and the puzzling results of experiments designed to measure the properties of electromagnetic waves. The behavior of light, in particular, posed a significant challenge to the established laws of physics. Experiments with prisms, diffraction patterns, and the spectrum of light revealed inconsistencies that defied the classical understanding. Light seemed to exhibit both wave-like and particle-like properties, a duality that classical physics struggled to reconcile. Experiments consistently showed that the speed of light in a vacuum remained constant, regardless of the motion of the observer or the source of light. This constancy was perplexing because it contradicted the principles of relative motion that applied to all other known phenomena. The famous Michelson-Morley experiment of 1887, which attempted to detect the Earth's motion through the hypothetical ether, found no variation in the speed of light, further deepening the mystery. This baffling observation set the stage for Einstein's revolutionary theories of special and general relativity. In 1905, Einstein proposed that the laws of physics are the same for all non-accelerating observers, and that the speed of light is constant regardless of the motion of the light source. This was the essence of his special theory of relativity, which introduced the radical idea that time and space are not absolute but relative and interwoven. These theories, published in 1905 and 1915 respectively, would shatter the foundations of classical physics, and introduce the world to the mind-boggling concept of time as the fourth dimension. Einstein's general theory of relativity further expanded on these ideas, describing gravity not as a force, but as a curvature of space-time caused by mass and energy. This new understanding of the universe opened up a realm of possibilities and questions, forever changing our perception of reality. Section 4. Einstein's Revolution. Time as the fourth dimension. Einstein's theory of special relativity postulates that space and time are not separate entities, but rather interwoven aspects of a single fabric space-time. This revolutionary concept challenged the Newtonian view of a static, unchanging universe and presented a dynamic, interconnected reality. In this new framework, time is not absolute but rather relative, dependent on the observer's frame of reference. This means that time can pass at different rates for observers moving at different speeds or experiencing different gravitational fields. This phenomenon, known as time dilation, is one of the most startling predictions of Einstein's theory and has been experimentally verified numerous times. Einstein's theory of general relativity further developed this concept, demonstrating that gravity is not a force but rather a curvature of space-time caused by the presence of mass and energy. This curvature affects the motion of objects, including light, and gives rise to the familiar gravitational pull we experience on Earth. Section 5. Visualizing dimensions, from strings to shadows. To grasp the concept of higher dimensions, it can be helpful to use analogies. These analogies simplify complex ideas, making them more accessible to our three-dimensional minds. Imagine a tightrope walker moving along a string. This string represents a one-dimensional world, where the walker can only move in two directions. The tightrope walker can only move forward or backward along the string, representing one dimension of motion. This limitation is akin to living in a world with only one spatial dimension. Now imagine a bug crawling on a sheet of paper. This bug's world is two-dimensional, confined to the flat surface of the paper. The bug can move left or right, forward or backward, two dimensions of motion. It experiences a richer world than the tightrope walker but still lacks the perception of height. The bug is confined to the surface of the paper, and cannot perceive the third dimension of height. To the bug, the concept of height is as abstract as higher dimensions are to us. Similarly, we, as three-dimensional beings, are confined to our three-dimensional space. We navigate through length, width, and height, but our understanding of higher dimensions is limited. We can perceive length, width, and height, but the fourth dimension of time remains elusive to our direct perception. Time is a dimension we experience but cannot see or touch. We experience time as a flow, a constant progression from past to present to future. This flow is continuous and unidirectional, much like the tightrope walker's path along the string. Just as the bug on the paper cannot perceive the third dimension, we struggle to visualize the fourth dimension. Our minds are not equipped to fully grasp it, yet we can sense its presence. However, we can use mathematical models and thought experiments to understand its properties and implications. These tools allow us to explore the nature of higher dimensions, even if we cannot directly perceive them. Through these models, we can begin to visualize and comprehend the complexities of higher dimensions. They offer a glimpse into realms beyond our everyday experience, expanding our understanding of the universe. By engaging with these abstract concepts, we push the boundaries of our knowledge and challenge our perceptions of reality. This journey from strings to shadows is a testament to human curiosity and the quest for understanding.